So I'm just going to say a couple words before we get started with the talk. Thank you all for being here and signing up for our inaugural Talkboctopus seminar series talk. And we want this to be, you know, a regular thing, and we want to invite a lot of really fun and interesting speakers that are in a lot of different fields and really exemplify the multidisciplinary nature of complex systems and data science. But we also want this to just be a lot of fun, so we don't want it to be super formal. And you know, we want to encourage you to ask questions. Speaking of that, you can either, I think for the purposes of this talk, probably try to save your questions for the end unless it's a clarifying question, and then we can try to write that in the chat and see if anybody else in the audience can respond to the clarifying question. And at the end, we'll have a little bit of time for a Q&A session. And for that session, you can either write the question into the chat box, or you can raise your hand and unmute yourself and ask the question directly. Just note that this seminar is being recorded, so if you prefer not to be recorded, please keep your video and your microphone off and only submit questions through the chat box. So yeah, and this will be available on our YouTube channel later, probably in a couple of days. And the last thing I wanted to mention is that we'll be sort of releasing the rest of the summer's speaker series shortly. So just keep an eye out for that in your inboxes and on Twitter. And yeah, I just wanted to thank you guys all for being here. This is something that I've really been wanting the last few months. I want to hear all of the interesting talks that I'm missing, that I usually get to have when I'm at conferences or in the Complex Systems Center, and we're all together giving each other talks about our research. So I'm really happy that we're all here together. So without further ado, I'm going to pass the mic to Peter, and he'll be introducing our first speaker.
Yeah, so I shouldn't talk too much, but I just want to say, yeah, Josh is a great old friend of mine. We did our PhD together at MIT. We're sort of part of a ramshackle group of students who were sort of lost in other disciplines and ended up working in a kind of complex systems group in the geosciences. So we've had a long history that goes back to the 90s, and you know, I've been greatly influenced in how I think about things and how I approach science in the world by Josh. I mean, he's an inspirational guy. So he's spent some time after MIT at Princeton, back at Princeton. There's a little shout out for you. Doing a postdoc there in ecology. And then went down to Georgia Tech, and he's you know, done a great thing, built a whole program, quantitative biosciences program, it's a PhD program. As we well know in our own experiences here, it's a lot of effort goes into that. That's you know, just really a titanic thing to build. It's the right thing to do because so much has changed, so much has you know, kind of exploded in terms of the way we can approach all sorts of sciences now. So, you know, really proud of what he's done there. I don't know how much Josh will talk about it today, but it'd be perhaps good towards the end if you could add something about it. But one of the things Josh has done is, you know, really try to get the story out in whatever he's working on through, you know, editorial pieces, trying to influence public policy, you know, in a good way, from a science-based way, and so we'll hear some of that today. But perhaps just, you know, if Josh could talk about, be interested to hear, like, just that kind of advocacy aspect as well. It really is important. You know, we try to do the right things with science. The science has to be right, but we also need to get our stories out. Something we think about a lot. And you know, Josh is a good example of this. So yeah, I think I'll let you go ahead. But yeah, you know, Josh has built a great program, great people down there. I was fortunate enough to visit in November, and you know, so excited to hear what he has to say today.
Thank you, Peter. Thank you, Jennifer. Can you hear me? And I'll just turn just a moment at my setup here, because I think you can. This is the official holder of this cell phone while I try to give my talk. So if I'm not looking straight at everyone, I have to kind of look at the screen, and I'll do my best. I'm very excited to be back. I was there a few years ago talking about viruses of microbes. And this time I'll be talking about virus dynamics in a different way. And I hadn't set up the talk to be as much about the interface between what we're doing as scientists and public advocacy. It's certainly something that I am increasingly involved in, passionate about, and try to do effectively and learn from others. And I think there's a lot we have to learn, but certainly in the case of COVID-19, a lot of what we're doing, whether influencing each other or shaping policy, the timescales of academic work are sort of out the window. And you all at Vermont know this well in terms of looking at Twitterverse and influence and so on. But you know, the world where I typically operate, thinking about viruses of microbes in ocean systems, where we're still analyzing data that was collected on a cruise many years ago. We're even thinking about phage as therapeutics. These are multi-year processes, and they should be. And everything is accelerated, and trying to do things in an accelerated manner, doing things robustly, rigorously, transparently is really hard. And so for anyone working in this space, I think some of you on this call are already doing that, you know that this becomes a third shift in a crazy kind of sense. There's an urgency, and hopefully increasingly models will be shaping in a positive way what happens, but also that means that you have to be willing to scrape a bit, whether communicating via Twitter or other social media venues, writing editorials, and so on. So I'm happy to talk about that later. In terms of the talk itself, not knowing the background of everyone in the room and not being able to read the room, because I can only see a few of you in these little pop-up screens, which is a disadvantage for fun talks in usual times, but it is what it is. So I'm going to try to cover a few topics, and Juniper, you'll interrupt me and let me know if there are questions that have popped up that are urgent, whatever the protocol is. So the title was Modeling Shield Immunity from Concept to Implementation. I added a few things, but I'm really going to try and give a bigger arc today. Part of the reason is that I think it's just important to get some of the context in place. And if I just jump right into this one topic, you kind of lose both why we got there, why we think it's important, why we're still working on it, but also a key message, which is even if we have this one approach that we're emphasizing in terms of an intervention, I want to be clear at the outset, it's not the only intervention type. And I think just like in thinking about climate wedges, that when one thinks about how do you deal with rising CO2, instead of thinking about silver bullets, if you think about a combination of approaches, each one's not perfect, but together they can get the job done. So let me try to get into the topic. Hopefully the screen moves ahead and I see it show up. So first of all, just want to thank folks who supported the work. And some of the folks have supported the work because they're just supporting us. And we decided in January of this year, we had to do something in response and told program officers. So if anyone is listening, thank you. We now have an NSF Rapid grant, so we do actually have some formal funds to go and engage in these topics. And also want to highlight, this is absolutely interdisciplinary work. It is not possible any other way, just because of the nature of our team at Georgia Tech, which involves folks from physics and quantitative biosciences and bioinformatics and computing and engineering and so on, but also because we're interacting with great people both at Georgia Tech and elsewhere, including people we've never collaborated with. A group, Ben Lotman's group, including Elisa Kroll and Kristen Nelson at the Rollins School of Public Health at Emory, precisely because of this nature of what we're doing, thinking about principles and trying to apply them. So thank you to everyone who's been involved. I also want to just highlight one opportunity, which is we are looking, because of the nature of our work in projects, all with this theme of how viruses impact and transform human health and the fate of our planet, and our increasing efforts to try and communicate these, not just to scientists, but to the public with dashboards, with informational reports, situation reports, as it were, to do that well and to reach all these different audiences, to foster team science. We are looking to hire a scientific project coordinator and data communication specialist, and it's on Twitter. So if you see my Twitter account, I've pinned that one, please spread the word. I will start screening applications in a few weeks, a little less than 2 weeks from today, and we are going to be hiring soon. So more information, feel free to reach out and hopefully get some a broad range of applicants, and for folks who really want to look for it and enable ways to get science out to serve the public good. Okay, so let me move back a few months, and it's more or less precisely 4 months ago. This was an early situation report that I shared at a talk on February 10th, because we ran a rapid response coronavirus forum at Georgia Tech in this process and already been working on R0 estimations. And this gives you some example of the case counts in the tens of thousands and 800 fatalities. And even just the image from the situation report makes it clear that the effort at the time was focused on Asia, predominantly China, and really East Asia. 2 months later, this is an example of the situation report. We're almost 1.5 million cases, 85,000 fatalities spanning the globe. And here the y-axis keeps going up, and this is just from today, over 400,000 reported, in other words, confirmed fatalities, and nearly 7 million cases. And I know Peter and many others have been wondering and worrying about even the accuracy of this information, right? Vis-a-vis underreporting. Cases in particular are deeply underreported, but even fatalities are underreported. This gives you just some sense of the spread and scale of what people are up against, what all of us are up against. So what I'm going to try to do today is really 3 things. For those who know a lot about epidemics, you will both find, I think, part 1 mostly kind of in your reserve tank. You know it already. And there will be parts that you might be annoyed with, which is fine, and maybe a few parts you'll be surprised with. And once I get those in place, I'm going to try to talk a little bit about efforts to control epidemics, and then focus in on shield immunity. So I'm not to say bearing the lead, but I am going to put a little bit later, just because I want to make an arc here and talk broadly speaking about COVID-19. And Juniper, so far you haven't interrupted me, but if anyone has questions, feel free to pop in. Okay, so let me get started. So very early on, there was some concern about how do we even think about what this is going to be? Is it really going to be this bad? Is this going to be like flu? And I found that this wasn't a quite effective way of communicating some notions of what was going to go on with COVID-19 in terms of this idea of a basic reproductive number, and we'll get into that number. It's not the only number that's relevant, and the fatality rate. And the idea is that if you're infected, there's a probability that an individual, this infectious case may lead to a fatality. Certain things like Ebola, MERS, and so on would have very high probabilities of fatality given an infection. Others almost are at 0. But of course, there's other issues here in terms of the overall impact, which is how many new infections are caused by a sick individual in an otherwise susceptible population, this notion of R0. And it's indirectly measured. It's very hard to measure it directly. We're often measuring cases, and you can measure fatality rate directly, at least some features. There was uncertainty about what that was, and I think we're zooming into something now, and there's still a lot of uncertainty. But the challenge was that it was both, relatively speaking, infectious, meaning it seemed to cause more cases on average, but yet not that as dangerous at a per person level, like Ebola, far more than seasonal flu, obviously far more than cold, and so on. And we've learned other features too. So it kind of sat in this weird place. Right? But the idea here is that we're trying to understand some notion of spread and some notion of significance, right? If it was spreading to a lot of people but had very low fatalities, we wouldn't worry about it. Right? And if it didn't spread to that many people, the individuals who get Ebola are very worried. I mean, it's very bad. We know that there was that terrible 2014-15 outbreak. But in terms of the overall spread, other features actually work against having global spread. So there's some features of coronavirus, obviously a respiratory disease with an asymptomatic route, that make it quite dangerous. So one of the things that we got interested at the beginning is how certain should we be about these estimates? Right? Here's some range, but how certain should we be? And what I want to share here is a bit of an illustration of why this is much harder than is generally recognized, even now. Here's a synthetic outbreak that I generated over a 150, 200-day period. And there is an example of a disease epidemic with R0 of 1.5. And here's one with 2. And here's one with 2.5. And I know that these are all 1.5, 2, and 2.5 because I built them to have these characteristics. And it's fitting exactly, seemingly, the same case data. And so this is not something that unfortunately is as widely appreciated as should be, that there's a difference between these case data and the strength of disease, and many kinds of curves can be compatible, or one curve can be compatible with many kinds of values of R naught. If I were to keep going in these epidemics, what you can see over a longer period of time in the simplified SIR model, there is a difference. And so I just want to highlight 3 terms that I will use: speed, size, and strength, to talk a little bit about epidemics. The notion of speed is essentially the exponential growth rate or growth rate of the disease. How fast do cases increase? This notion of size could be a peak number of cases or a final size, however fraught that might be in inferring it. And strength is some individual level view of how individuals are likely to spread on to other individuals. And you can see in this particular example that there's not a one-to-one relationship between speed and strength. And so in thinking about how we worry about control, we're trying to infer strength from speed, from what we measure, and trying to use that to get some notion of how bad things might be, all caveats notwithstanding. Okay, so the key point here is that many values of R naught can be compatible with the same observed rate of increase, even if the projected outbreak sizes are different. And so early on, there can be a lot of confusion. And just to understand that, here's an SIR model. And I'm going to ask that Peter not go insane when I explain some of this. Don't worry, I will mention other things. Hopefully that will make you go less insane. I do think it's important to explain these concepts. So we have these classes and compartments, and that's, yeah, right, see, you've gone insane. That's good, that's good. Let it out, let it out. Scream into the mic, but you're on mute, so it's fine. We have population classes, and that's true also even in network models, that we're essentially distinguishing individuals by their disease status, whether they're susceptible, infectious, or recovered or removed. When there's contact between infectious and susceptible individuals, we get new infections, and the infectious individuals recover. And so we have these 2 processes. And the reason why people often talk about R naught as this threshold and why it's given so much importance is the expected number of cases changes exponentially in theory, where whether or not it grows or declines is whether or not the number of new cases exceeds 1 on average. Okay? Now, the R naught is really infections per time times the infectious period. And I've just said all these things. But this does explain why you can get different values of a growth rate with the same value of R naught, because you see we have 2 variables here, this sort of infection rate and the infectious period. And we have one thing that we're measuring. So there are different combinations can yield the same output. So when people at the very outset of studying COVID-19 began to make these estimates, they use a lot of different model types, branching processes, SAR models, network models, etc. But essentially, they were all looking at the same data set, which is cases, and trying to figure out what this R naught was. And if you see on the left, they didn't all agree, right? Anywhere from 1.5 up to things like 6 or 7 or 8, right? And in fact, incompatible confidence intervals. And it turns out what they were really doing, in our view, is making latent assumptions essentially about the dispersion, how variable the time is between when an individual is infected and when they infect someone else. And I know in the complex system worlds, you often think about dispersion in terms of networks or in terms of infection rates, that some people infect many people and some infect very few, the sort of 80-20 rule or 20-80 rule, depending on which way you like to count things, that 20% of people may be responsible for 80% of the transmission. But timing can also be dispersed. And in an SIR model, the notion is that you have an exponential duration of being infectious. In an SEIR model, you first have this exposed class and then an infection class, and you get this gamma-like distribution. And without going into all the details, you can see here that not everyone agreed. Some people felt there was a lot of dispersion, some felt there was very little. They didn't agree on the generation interval. And these things end up meaning that you take the same observation of cases and you get a different reproductive number based on these latent assumptions alone. Okay? And to make this absolutely concrete, there's something we talked about last year in work with Sang-Woo Park and Jonathan Dushoff, David Champredon. Imagine taking the same data. This is this curve here, which is weekly incidence, so it's going up exponentially. And if there are shorter generation intervals, meaning that the period of infectiousness is shorter. This means that if you're inferring R0 from this same curve, you get a lower reproduction number because it took more generations of reproduction to make the same output. Whereas if the generation intervals are longer, then there were fewer generations, because remember, it's during an average infectious period to reach the same case value. So there's a direct relationship here between latent assumptions and why it's not just a matter of figuring out the number of, let's say, the strength of transmission, the force of infection, but this duration matters, and the variability of duration matters as well. And this also helps, once you know this, you can start to parse through Forbes-like headlines. The COVID-19 coronavirus may be twice as contagious as we thought. And this will keep coming back. Usually in talks, I don't do as many headlines, but there's absolutely an information spread that goes along with the disease as well, and then can influence the way people act. Here's an example. Again, this is published in July 2020. That's not really true. It just came out and they put it in a future journal. So it was from the past to be published in the future, but it was available in April. And what you can see here on this left is that you have R0 versus the growth rate. And then you have these different curves. They claim that R0 was about 5.7. I mean, that would be very difficult if the average case was producing about 6 new cases. And that's more than twice as difficult than we think things are, and it would be very bad. But really what was going on is they measured growth rate and then assumed long what they call serial intervals. And I'm not going to go all the details of serial versus generation intervals, but serial intervals are the time between when someone, the infector, has symptoms and the infected gets symptoms, which, by the way, can be negative and is negative for COVID-19, which I will return to sometimes. But if you assume that's longer, there's a relationship in some sense implicitly with generation intervals, the time between when you're infected irrespective of symptoms and when you tend to infect someone else. And if you make that longer, you think that R0 is higher. It's the only way to make sense of the observed data, okay? So this also begins to you start to realize that some of these claims are really about assumptions. And if we can reject those assumptions, we can also reject this idea that instantaneously it became twice as contagious. No, we just made an assumption that the duration was very long. We've had fewer generations to make sense of the cases. And this is a quite technical slide, and I'll just take away the point, which is what we tried to go through all these latent assumptions and just try to figure out what was a compatible R0 with a confidence interval that made sense given different latent assumptions that we're not sure which one is true, but given the assumptions that were made. And the takeaway here is that individual point estimates can be much larger, and we also began to understand really the driver of uncertainty. And one of the key drivers of uncertainty is going to be the generation interval, and the other effect will be, all things being equal, if you have more dispersion, there can often be earlier transmission. So that tends to have an effect. And you can see on the bottom left that R0 is driven by increases in the mean generation interval, in the growth rate, but also can be driven less by increases in dispersion. So the caution here is I've talked about speed and strength, and I'm not going to go into size because obviously we don't know what the final size of this epidemic is going to be. There are many other things that go beyond networks and so on. I just want to point out that there are many reasons to think that these classic SIR-like models, which produce things like 60, 70, 80, 90% infected as a final size, will not be the case, and may not be the case even in the absence of large scale, let's call it closures, or even the absence of therapeutic interventions and so on. One reason is simply that people tend to react to others being sick. And so in some work we did last year, we have similar work ongoing now. If people remember that there was this danger and then change their behavior and sustain change behavior, so it is a form of sustained social distancing, but not necessarily with a lockdown in place, you can end up having the same initial beginning to the epidemic, but very different outcomes. So significant overestimates of final sizes, even if things look the same at the outset. And Laurent, I just stole a slide from your work, again, looking at the proportion of susceptible of individuals infected, in other words, final size, and comparing these classic Kermack-McKendrick-like models versus though with a network model. And I think your point, and one that I tend to agree with, is that the SIR-like models tend to overestimate final sizes. And there's a lot of variability in these final sizes. And it's possible that this has to do with dispersion. The fact that, again, individuals who have many contacts tend to get sick earlier, and then they, in some sense, are not able to transmit onto others. There can be paradoxical effects. I'm happy to talk about those. Or you can invite Laurent and colleagues, and he can talk about them some other day. So that's what I wanted to go through with the first part. And I'll just pause there. And I haven't seen questions pop up. Okay, it's all clear. Good. So I will now talk a little bit about dynamics and control and then get into shield immunity. And maybe I'll move a little bit fast through these. Again, going through this conditions for epidemic growth, although it's simplified, I find it beneficial to think about them because it gives you some idea of the factors underlying or not, whether in this SIR sense or even a network sense, gives you some idea of how people think about control. How do we reduce the infectious period? Well, maybe we can treat people. How do we change the infections per time? Well, maybe we can reduce contacts by infectious individuals by contact tracing and isolating them. How can we stop them from interacting with susceptibles? Maybe we can potentially quarantine or have lockdowns, or maybe we can even do things as we propose, like shield immunity, by changing the interaction rates of those who are not recovered vis-a-vis those who are. And then, of course, there are things like masks, which is even if there is an interaction, you reduce the probability that the contact transmits the disease. So these are all tiered layers of ways to try to reduce the number of new infections. And just to understand, because I think there's a lot of misinformation and confusion about it, at the very early part of 2020, there was a prediction that in the United States, there was a potential, if an unmitigated disease were to spread, we would have something like 2 million plus fatalities. And I think, again, this Imperial College of London model has both been good and bad in some ways, but overall, I just want to explain the rationale behind this estimate, which is that if you have a disease that has R0 2.4 in this mean field with 80% infected, and we can question whether or not that's 3- or 4-fold above because of networks and all other reasons, what they're saying in essence is that you take a population of 330 million with a large number of fraction infected, with something like a 1% infection fatality rate, and you get that number. You don't need to even understand all the complicated details to understand that is the sort of scale. And at least right now, this number of a little bit less than 1% infection fatality rate is, I think, holding up. It's holding up to scrutiny. It's obviously has a massive difference with age. The infection fatality risk for someone who's young is almost negligible. For those who are 75 and older, it can exceed 25%. So there's a massive difference there, which I will get to later. And this means in some sense that models are going to inevitably overestimate whether it's Ebola, this was from 2014, or coronavirus. They're going to do that because the point of these models, and I think the Imperial model and even models on networks, and what we're trying to do is not to be right with a bad outcome, but to avoid bad outcomes and try to change trajectories. And so that really, I think, is the model purpose, to explain these different outcomes. And as you all know, we got into flattening the curve and then crushing the curve and so on. And I'll just say one more thing about that, which is there was a period, and I think that's still now, which is there's a large push to say, don't believe these models. Look, they said 2 million cases, 2 million fatalities, or something terrible was going to happen. It didn't happen. And so therefore we shouldn't believe it. Well, no, the point was that they were trying to avoid bad outcomes. And now with efforts to open up, I think we're beginning to face the reality that we remain largely susceptible to infection. Okay. And I want to talk about this before I get into the shield immunity component. And I don't have a watch here, Juniper, so you'll have to tell me, how am I doing on time? What time is it?
It's 12:30.
Okay, we're doing fine.
Yeah.
Good. So what evidence is there on the impact of interventions? Sam Scarpino, your former colleague, who's now at Northeastern, worked with a number of folks to estimate the effect of this cordon sanitaire in China at the early outset. And one of the things they did was to relate essentially the mobility and the number of cases. And what they showed early on is that there was a very strong correlation between essentially where people were moving and where cases were appearing, in part because cases were being imported, and so you'd see a lot more cases as people moved, often were sick, and then began to transmit. Once the cordon sanitaire was imposed, this led to a rapid drop in cases, and then a lack of, essentially the absence of correlation between these two metrics, and you can see that on the left as well. And so essentially what they're trying to say is that by taking early steps, stopping importation, and doing rigorous control can make a difference. But you have to do it early. And I think New Zealand is a great example, right? They are at, as far as I understand, 0 cases, not just 0 fatalities or 0 cases right now. But if you don't do these things early, and admittedly an island nation with advance notice is different than other places. Nonetheless, what they also are trying to say is community transmission becomes the dominant factor. That at that point, if you start having travel bans and all these bans on movement, in some sense, you're focusing on the wrong thing. The dominant mode of transmission becomes community transmission. And obviously that's what we're facing. What are the effects then of lockdown and other ways of severe social distancing? This is from a French group led by Vittoria Colizza, who's a member of your network complex systems community, who tried to estimate what things would have happened in terms of clinical cases or percentage of infected population, focusing on the Île-de-France region in Paris and around. And essentially their takeaway is that these interventions rapidly shifted the curve from perilous exponential-like growth. So fast doublings, and if you recall, cases were doubling every 3 or even 4 days, around that amount back, in some places in March or even in February, but certainly through March, to a different trajectory. And so averting significant new cases, significant hospitalizations and mortality. This also came out in late March, and it just was published yesterday in Nature. This is by the Imperial College of London group, led by Sam Flaxman. And their estimate, even then, was tens of thousands of fatalities. Now, because of delays, they're claiming essentially the prevention of millions of lives net. And I think that's important to keep in scope. What I hear when I hear claims like this is that these early interventions stopped rampant spread. The question I think that is difficult, maybe impossible to answer, is how does a lockdown do it versus telling people to wear masks or change behavior and so on? And I don't know if that's an answerable question, but I think it is answerable and knowable that in terms of initial spread, and you can see the difference between certain countries, we can get into how much impact it's had, but there are differences between New Zealand, which is around the size of Georgia, which has had very few infections and cases, and we are over 2,000 fatalities, which is probably an underestimate, with no signs of abating. So clearly there are differences in terms of taking these aggressive approaches. And how much of this is sustainable, I think, becomes one of the deep questions, and really one that's worried me from the outset. Part of the reason why I think this is very hard is that there is an asymptomatic route. And I'm going to say there is an asymptomatic route, despite the fact that yesterday the WHO said such routes are very rare. And I would like to think I understand what they meant, but I don't necessarily think it was helpful. And I think by today they've already walked it back. When I think about transmission, I think of it through the lens of a system in which you have susceptible individuals, whether this is in a network, whether it's in a meta population, whether it's in a well-mixed population, wherever it is in terms of these states that someone is exposed, they become symptomatic, they may be asymptomatic. There's also, you can think of pre-symptomatic states, which I didn't include here. Someone's asymptomatic, but still infectious, and then they become symptomatic and also infectious. And some of the symptomatic cases become severe enough that they have to go to a hospital. Some of them are subcritical, some are critical, and some of the critical cases lead to fatalities. Now, this is a still a simplified approach. But the key problem part here is the asymptomatic route. Okay? And so one of the things that we did early on was to ask the question, how much does the asymptomatic route influence the strength of the epidemic, and how much is unknown? And in doing so, we recognize that the change in susceptibles, you can use something called a renewal equation formalism. The change in susceptibles is going to be decreasing due to new infections. And those new infections are because individuals were infected a while back, some time ago, and they may have been asymptomatic or they may have been symptomatic. And they have different generation intervals in terms of how likely it is that someone who's asymptomatic is going to have a new transmission a certain time forward. Maybe asymptomatic cases are short and are going to resolve very quickly, but maybe there's more of them. And so we have to try to reconcile the fact that what we're observing are cases, but the generation intervals of asymptomatics and symptomatic cases may not be the same. And without going into all the details, what we learned is essentially that the duration and the proportion of asymptomatic transmission matters. And so what I'm showing here on the y-axis is a notion that there may be a probability that if you're infected, you have an asymptomatic case, anywhere from 0 to 1. And it also may be that the duration of those cases relative to symptomatic cases may be short, which is on the left, or long, which is on the right. To the extent that there are often asymptomatic cases and they resolve quickly, they do transmit, but they resolve quickly, that means that if we try to figure out naively what R0 is based on data, we'll end up overestimating it. The true value will actually not be as bad. Whereas if they tend to be longer, right, they're not severe, but they're longer, but sometimes lead to severe cases, and they are disproportionately the outcome of transmission, then we could be underestimating cases. And so one of the things I think I want to take away here is that really asymptomatic transmission is a double-edged sword. It can lead to many more cases, but cases are not as bad. And so one of the things that worries me, has worried me from the outset, and I'll just put it out there, we don't have an answer, we're trying to figure this out, is what is the extent to which if someone has an asymptomatic case, if they infect someone else, is that person more likely to have an asymptomatic case? If someone is a symptomatic case and severe, is the person they infect more likely to have a symptomatic and severe case? If that's true, then many different things can happen. It's very hard to figure that out, but I think it's worth figuring out. We're trying to work on it. And part of the reason is because you can have even longer cryptic chains, right? Essentially, where asymptomatic are propagating on to asymptomatic cases, and then all of a sudden, maybe you interact with someone who's older, they have a severe case, and now you have a severe chain. I don't know if that's true, but I certainly know that this asymptomatic route from the very outset has been problematic, has made things harder to deal with. And I will show in a moment some more about this. And I think this is important. It was part of the reason why yesterday I'm thinking about this talk, and I should just talk about shield immunity. There's so many other things to talk about, and they're all linked together. This was a WHO report that came out in CNBC. Spread of coronavirus, very rare, but experts raise questions. And then you can see on the right, it's done now. Asymptomatic transmission, very rare. It's just done. And that only took a day, right? WHO says rare. Then your clarification shows up. Unfortunately, whether it's this message, or other crazy messages on misnarratives, and Peter and you all may know this better than me, it would be very interesting to know when people get doxxed, and I bring that up because it was an unfortunate case of doxing this week of an incident related to a violent assault on a bike trail near my family home in Bethesda, Maryland, and someone who did not do it was doxxed. The number of people who hear about that versus the number of people who hear, oh, that person wasn't the person, there's an enormous gap. And so it's challenging to communicate in these moments because once the wrong narrative gets out, it spreads very quickly and the correction is just sort of buried somewhere and forgotten. And so I just want to make a point in this talk. I know it's in the middle and this probably won't go viral, but asymptomatic, pre-symptomatic, mild transmission, as far as I can tell, and the evidence bears out, is real. I'll give you just two examples. And I know these are inferred, one of them from model cases. In a work by Gabriel Leung based in Hong Kong, they tried to figure out what are profiles, and these are profiles with respect to the days after symptom onset, of the infectiousness of individuals. And the point you should take away is that these curves often sit at negative, meaning before you can see the symptoms, they seem to be infectious. Right? That's the point. In other words, this would be pre-symptomatic infection. There are other cases in which the transmission or the symptoms may be so mild that during the time that you have those symptoms, you wouldn't think that they're COVID-19. There's nothing specific or severe about them. Later, someone might say, well, now that I know you were infected, I realize that that was a symptom. That's very different and may be classified as asymptomatic or mild. Another example of these negative serial intervals is from Laura Meyer's work, again, published in CCEID. And if you look, this is not a one-off event. It's not very rare. Right? It happens where you have essentially the person who someone infected has a symptom at the same time as the infector, which is a 0 serial interval. And yes, it's shifted to the right. It tends to be delayed. But all of this is consistent with the idea that pre-symptomatic infection, mild transmission, is a real effect. And I just want to make points. This has happened multiple times. Masks aren't effective. Oh, whoops, well, they are effective for other diseases. We don't have definitive proof. We don't have the evidence yet for SARS-CoV-2. No evidence antibodies confer immunity. Well, for SARS and MERS, that's 2-3+ years. Have we proved it yet? No. Is it provable that there's 6-month immunity? No, it's impossible. We haven't had 6 months of cases, or won't have till soon. But there's lots of evidence. And I guess the same thing is happening here. So it seems disappointing, and it's a trap. I don't know how to get out of that trap, but it's a real trap.
Josh,
So
we have a couple of questions
yeah.
about your last slide. It drummed up some discussion.
Okay.
If you want to wait till the end too, that's totally fine. But Sam Rosenblatt asks, what would be the mechanism in the case where asymptomatic cases are more likely to lead to asymptomatic cases?
So so let me go into, we're beginning to work on this. So anyone wants to join forces and try to investigate this, we kind of understand what this would look like epidemiologically, because it implies almost like 2 epidemiology birth states using a next generation matrix approach. But from a mechanism, let's say an individual, there's a relationship between the dose and the outcome. And so if one thinks about an asymptomatic case as not having some relationship between severity of symptoms and viral load, then low viral load, low symptoms, I spread to someone else, low dose, and there could be a relationship between within to between transmission. I realize I am hand waving. Mm-hmm. Whereas, and I think, Peter, you've worked on this too, this notion of dose. If you're around someone who has a high viral load repeatedly, then you're going to get a larger dose. And if there's some relationship between dose, and it may not just be single, but a repeated exposure, then that could again imply some sort of relationship between the within host dynamics and between. Have we done this? No. And I was thinking about not even bringing this up today. My view at this point is that ideas are cheap in some sense. We actually have to do stuff. And so I'd much rather raise that question if someone has this or is looking at a relationship between severity of symptoms and onward cases. I've been wanting for a while to take a look carefully to see if there's any evidence in the data that there's some relationship there. But mechanistically, I view this as a viral dose argument. I don't know if that satisfies that person, but I don't have proof of it yet or evidence, but it's something that I've been curious about for a while.
Great, thanks.
Should I keep going, or was there more?
There is another question. So somebody is wondering if you think that asymptomatic people transmitting to other asymptomatic people and symptomatic people transmitting to other symptomatic people would indicate that there may be 2 different strains emerging.
Right. So I think that could be possible even without 2 different strains. We know there's a lot of strains that are out there already in the sense of sequences that are different. And I don't have any evidence, and I'm not the right person even to ask to know that those lead to any phenotypically different outcomes. But I think it's possible even without that, to have those sort of outcomes just from a dose response. It could also be something that there's not necessarily this direct mechanism of within to between hosts, but rather some mixing patterns could lead to the same outcome even without that. So for example, older individuals are more likely to have bad outcomes. And if they mix with older individuals, then we might see that there's an age-dependent effect where severe cases lead to severe cases because old people mix with older people. And younger people who have less severe outcomes mix with younger people. So if you had some assortative mixing in some way, that could also do it. So I think there's lots of other ways that this could happen. And I think it would be very hard to figure out mechanism, but in practice, one could end up having this sort of effect, whether from a, let's say, within host biology mechanism, assortative mixing mechanism, even before we get to the different strains and, mild and severe strains that I haven't seen any evidence of at the moment.
Great, that was the last question.
Yeah.
Can I just quickly say, Josh, it seemed to us, this is years ago now, the dose aspect of all of this is incredibly important, but I'm talking about the early 2000s, but just there wasn't a lot of data. It's a hard thing to study. But we kind of married biological and social contagion together through that idea. Obviously propaganda and story spreading and so on. Dosage is really key.
And there's this whole notion of infectious dose, generally speaking, in microbiology and epidemiology, that's often not well understood. Why some things take a few, this is often done for bacteria, it takes a single bacteria in some cases, but others tens of thousands, right? Why is that? And these are hand-wavy arguments. I mean, it's fascinating. And I don't know if we know enough to make a link between dose of SARS-CoV-2 to outcome. But I think it's important to think about, because if there is a relationship, it could lead to these kind of effects. And anyway, so I'll leave it there. I should probably move on just to get to the last stage.
I like the way you frame those things. Okay.
Okay. So let me now talk about long-term strategies, because for those of us who aren't dialing in from New Zealand, we have to think about how to get out. And even New Zealand has to think about how to sustain where they are. And I say this in the absence of pharmaceutical interventions, right? Because if we wait for those things, we will be waiting potentially a very long time. And I hope they come, but we have to act as if they will not in the near term. So this goes back to the Imperial College of London report, a projection of a potential second wave. And I think this is an oversimplification in many ways, but the idea is that if you do a good job of suppressing through the summer, which clearly we've done a okay job, and in many places not nearly as good a job as one would have hoped, then still this means that the effectiveness implies that the vast majority of people remain susceptible and therefore at risk for a resurgence of cases. And this has led to a zero-sum dichotomy, where, as you see in the upper right, was the Dow to die for today or what? And you might remember the dying for the Dow memes of a few months ago. That still is in play, I think, because there are real costs of socioeconomic pain with respect to places. And this was brought up, that if you're in a place that has done a relatively good job of control, you haven't seen the impacts like New York or in some other places where there's been severe impacts. And yet you're still feeling all the economic pain and you're wondering why. Right? And so there's this trade-off here between infection control or rather than somehow doing both. And one of the things I think fed into this was this notion that, look, well, if we just kind of do what we're doing here, it's going to go away, right? And I am going to take a few slides just to mention the fact that in March 28th, the IHME model, which for a while I'm not sure is any longer, was being used by policymakers to make pretty big decisions. And there was going to be a peak in April 15th, and then it was going to go away. And if you notice here, this was an update. They made some changes and some kind of crazy uncertainty curves. There's no uncertainty after June 1st. Like, it all goes away. Here we are right now, absolutely no uncertainty. That's problematic. It's problematic because there should be more uncertainty in the future. And I think let's keep that in mind, even for those of us who are coming up with strategy interventions. There are a lot of things we don't know. And buyer beware, I've said this before, but these projections and the reason why that they're so certain in the future is essentially they use a non-mechanistic model, a functional form, where essentially the death rate goes up and down in a Gaussian-like manner. And because of that, it must go away at a certain future point. You're using current data, and there's a unfortunate cautionary tale from the late 80s, early 90s on HIV projections, which turned out to be incredibly wrong. And these two, unfortunately, the same thing has happened. Using these non-mechanistic curves, assuming that early dimes are going to be symmetric, and there's no rule that says that epidemics have to have symmetric shapes. Here's some from just a couple days ago. On the right is joint work with Sungwoo Park and Jaehoon Exon, Jonathan Dushoff. We've updated this more recently. These are fatalities, daily number of reported deaths over a multi-month period in 50 states plus territories, with a few countries up on top for context. And whether or not this is precisely the right granularity, you can see that with the exception of a few, and New York has gone up and gone down, though has a shoulder-like phenomenon. Many places look like they've entered plateaus, where cases go up, fatalities go up, and then stay there for a long time. I want to point out that we have a meta-archive paper that we're in the process of revising, in which awareness of the severity of disease, and we're measuring severity here in terms of fatalities or severe cases, just because people don't change their behavior because of cold. You have cold, I have cold, we don't really change. We change because of a very rational fear of not getting sick, hospitalized, or leading to a fatality, whether for you or someone you know or love. And so in these simple models, if there's feedback where people distance in the near term or the long term, it can make a massive change in the shape of these trajectories. And if they're responding to near-term dynamics, in other words, things seem very bad now, so I should keep avoiding interacting with other people, you get generically these shoulders and plateaus that can last a very long time. And unlike the peaks of the IHME model, these peaks are nowhere near herd immunity. Almost everyone remains susceptible, yet we seem to be at a kind of a plateau. And we can get into whether or not these are compatible or the right explanations or so on, but I think clearly people are making changes before lockdowns were in place and are not going back, like in Georgia, to normal even after lockdowns are lifted and we're supposedly back at business getting close to normal. Other folks have thought about one-year timelines, and I won't go into this otherwise, just really thinking about how we're going to modulate over a long period of time. And I'll mention also this work by Christoph Fraser, thinking about testing and tracing as one that's critical. And here I highlight this just because, at least in Georgia, we've far too long thought about testing as an indicator, like keeping score of the epidemic, how we're doing on the epidemic today, rather than using testing as a means from the very outset to identify people who are sick as quickly as possible, find out who they interacted with, quarantine them, and then test them so we stop transmission chains, rather than it just being a passive indicator. And the point of this paper by Christoph Fraser is that time matters. The faster one moves to isolate and contact trace, the better chance one has of actually turning disease dynamics around. There are many more ideas here, symptom tracker acts and work shift theories and blah, blah, blah. I'll just make a point that there's not a one-size-fits-all solution, in part because where we are very different places. What one should do when there are very few cases is very different than when, unfortunately, there are many cases. And it's the latter that I'll wrap up with. The bulk of interventions really focus on reducing new transmissions by closures and or tracing. But we're at a point now where many have been sick and recovered, from a few percent, 2 to 5% in places, to some in excess of 10 to 20% in hard-hit places like New York. Could these infections, where we're still potentially far from herd immunity, help reduce collective risk? And so this is what I'm going to wrap up with here. I think I have about 10 minutes left or so. Good. It's a concept of what we term shield immunity. The idea is that susceptible individuals interact with infectious individuals, and then they themselves recover. If recovered individuals, those who are PCR negative and serological positive, were to either increase their interaction rate or substitute for interactions between S and I individuals. In some ways, buffering and protecting those potentially dangerous interactions, we could have population or collective benefits, not for the individuals recovered. They're already recovered and we're presuming protected from reinfection, but rather reduce onward transmission risk for others. So that's the concept, and in a very simple sense, you can see it already in the model above, where there's some sort of elevated interaction rate, which we call shielding by recovered individuals, and we want to see what effect this has. So what is shield immunity in a network sense? And I'm going to try to highlight a few things that we're doing here. We have unknown infection status, and we've reacted in some sense by taking extreme social distancing steps, cutting off potential contacts. What we're proposing is that at a certain period when there are enough unfortunate individuals who've been unlucky enough to be infected but lucky enough to have recovered, that those individuals, if they could preferentially interact, then that could essentially lead to fewer interactions with you, this person who's maybe still susceptible, with infectious individuals. And again, the scale and type of testing matters. From the very beginning early, we've been trying to promote the idea that serological testing is going to be key. A, for the reasons of getting the denominator understood, so we can figure out really what the infection fatality rate is, how you've been infected in the past, rather than are you shedding virus now. But also because we view it not just as a passive indicator. Just like PCR doesn't have to be a passive indicator. Our argument here is that serological testing may be used actively as part of interventions. And for those who study any of the epi literature, you may recognize some of this similar to cocooning and pertussis. The idea that there are ways in which we're trying to protect individuals. Here we're trying to do it in a very different context because of the nature, not just for a limited group, but for a larger group. I'm going to show the SIR version of what shield immunity does. There's a lot more details here. The idea is in a standard model, you have susceptible individuals have some exposure to infectious individuals, and you then have onward transmission, they recover. Once we explicitly write out the contact rates and we elevate the rates of interactions by recovered individuals by this factor alpha, instead of dividing by n, you end up getting, which in a fractional sense is just 1, we end up getting 1 plus alpha r. So you should think of this in some ways as an infectious individual is interacting with a certain number of people. In a well-mixed sense, they're interacting with a S over n number of susceptible people, but if the recovereds are interacting, we're weighting it by interaction rates. So we end up diluting out those interactions. And what you can see here is that in terms of these mean field models, the epidemic size goes down rapidly. And there are different versions of this. In the fixed shield mechanism, it means that not only do recovered individuals increase their interaction rates, but the total number of interactions is fixed. So we're sort of doing the same amount of work, but just shifting over more to the recovered individuals. And you see a dramatic decrease even at relatively low shield strengths. We also did this in more complex scenarios. And the takeaway there is that this sort of shielding can be used synergistically with social distancing. So in order to get the same relative reduction in total fatalities in one of these complex COVID-19 models, you can use less intense social distancing. So here, that's the rows, or the y-axis. So decreasing social distancing, if you go across with shielding, you can end up getting the same relative reduction which you see in these isoclines, while without having to use such extreme social distancing, which have different effects. This is an example of the kind of dynamics that we see with deaths per day, ICU beds per day, cumulative fatalities by age. And this will become important here as I move in the last 5 minutes or so. These are all dynamics in which there's a baseline case and the different levels of shielding, so it both foreshortens and makes earlier the peaks, but also reduces them. In all of these cases, with an age structured population similar to what we have in the United States or in Georgia, the bulk of fatalities are going to be in older individuals, even if the bulk of cases are in younger individuals, just because of the nature of the infection fatality risk. And that's going to be an important of where I think we're trying to go here. What we then did was we asked the question, what happens if we take our effort? And I know this is a bit complicated. And the takeaway point here is, let's say we take our effort of shielding, but direct it at older individuals. If we do that, that's what I mean by optimize. We can even further take on benefits. So instead of shielding individuals interacting with everyone irrespective of age, if they focus their attention on older individuals, and we'll get into a practical meaning of that in a moment, then we can even get further reduction. So at least in theory here, the amount of recovery that we have now in some places, above 5 or 10%, can be a condition in which this could be done in practice. The question we have had, though, is it feasible? And someone just, ooh, a line just showed up on my screen. Is it feasible? One of the ways we've thought about feasibility is to actually think carefully about test status. So the top panel shows an SEIR-like model with a hospitalization class, but we've divided up test negative from test positive people. People who take serological tests, and it could be because tests are not 100% specific. It could be that you could be positive even though you haven't recovered. That would be a false positive. And that would be bad vis-a-vis shield immunity. Whereas the dashed lines move individuals who are recovered into the right categories, into this recovered shield class. So what we've done here is include these features like age stratified risk and using real analytical features and ask the question, what would happen if there were both false positives and potentially false negatives in a shield immunity strategy? And the idea is that shield immunity is going to, in our view, become important if we begin to test people and tell them to go back to business as normal. Here's a no shielding scenario where the bottom panel is proportion of the population completely released from social distancing. So these are things that you probably have heard about, like immunity passports, which for various reasons in an essay that I haven't finished yet, I prefer calling immunity visas, because there's no evidence that we should think of these as a 10-year guarantee, but rather a short-term state that needs to be renewed and revisited. We learn both for science and also be more realistic for various reasons. The point here, though, is although people are going back to work, if you look at fatalities, what you see are these little curves going up. And the reason is because there are individuals who sometimes are false positives. If you just tell people to go about as normal, it doesn't actually help. You're just releasing more people, essentially relaxing social distancing. Whereas if there is some shielding, what you see are these curves going down. So you're releasing people, but what you can tell is that in these high performance assays, we're now at the point where specificity exceeds 99.5%, and some of them are upwards of even of that. Then what you're seeing is actually further decreasing in cases and fatalities. And once you get into this monthly or quarterly level, you're beginning to strike a balance between trying to foster economic engagement, meaning getting people back to work safely, as well as reducing fatalities in cases. And that's what we show here. That when we look at relaxation of social distancing and testing, we find we're looking for blue on both. The idea is that some social distancing and shield immunity, given feasible testing, could lead both on the left to a decrease in deaths, those blue regions which are on the top. Obviously, if everyone social distance, that would be ideal, but that is not sustainable. But also a number of release, which you can see is in the upper right, where essentially everyone is relaxed from social distancing, but there's a compromise in which there's overlaps of blue on both. And so our view here is that there is a way to kind of do both, not perfectly, but even with imperfect tests. And I think, do I have time or have I already gone over time? I may have gone over time.
You're a little over, but it's okay.
Okay, well, I have just this last part, which I realize I maybe put a little bit too much preamble stuff. And apologies. We have been thinking about this in practice. And Peter, do you want me to hold now? And I can hold.
I just want to say you're just a skosh over the 30 minutes you promised. So
okay,
it's fine.
Oh yeah, that was between you and me. I decided not to do that talk, and I'm sorry. Maybe I should have done that talk. Okay. I had to cut you off when you were in Atlanta, so now I guess this is what we do to each other. Oh. Let me just point this out because we have been thinking about implementation. So I do want to just say this last bit, which is in order to do this, these population scale things are hard. It's They're harder now because of the government we have. If we had a government potentially that I felt was a responsible actor, I might be more excited about a nationwide program, but now I'm a bit less excited for various reasons. Therefore, how do we even think about how to implement programs that could work, and where should we put our effort? One of the ways I think we should put our effort is thinking about this in terms of networks. If there is a shield and elevates an interaction with someone, we've asked the question, if that person decreases interactions with others, what would happen? And so what we've done is take these sort of networks and take the shield immunity idea and show that it actually can work in theory with small networks in which you essentially are substituting interactions that individuals preferentially act with these shields as long as there are a certain percentage of them. And you can see here that rather than have final sizes, which get to be something like 75 or 80% in these small networks, you end up getting something closer to about 30%. So there's a significant decrease, or even 25%, excuse me. So a significant decrease in the number of cases. And the key here is these shielded edges have higher weight and other people are decreasing in interaction. So that's quite key to the finding. There was a visualization, but I'm going to skip. Good. And just to say where we're putting our initial efforts. Let me see if I can get this. This is the last real slide. In Georgia, there's been over 50,000 reported cases. We think that's probably a 10 to 1 undercount, and over 2,000 fatalities. In Georgia nursing homes, there are over 1,000 fatalities. There are essentially half the fatalities are in nursing homes. And in our view, this is something we're trying to start. And again, we'd welcome input, collaborators, help, and even caution. Can we develop shield immunity protocols to reduce risk of new infection? I want to point out that there are about a third as many reported staff cases as confirmed cases. So many staff have had infections, many asymptomatic. How can we leverage recovery of both in a network context? How do we retest to understand whether or not these things are actually making a difference? And our next steps, and again, I'm putting this out there because I welcome feedback and because I think this problem is too big for any one group alone. We're thinking about these networks as really bipartite networks with residents or patients and then healthcare workers, knowing that there is some ability in a informed, trained hospital or nursing home setting for individuals to actually change who they interact with. And given that there's infection controls already in place that people aren't grouping together, we are concerned that most of the new transmission may be due to interactions between individuals who are infected, perhaps asymptomatically with mild cases, interacting with a resident, and that's spreading to other residents back via nurses or healthcare workers. And so we are taking steps now to begin to build these bipartite network models as a means to reduce significant impacts. And I'll just end with that. We're not going to have certainty on COVID-19 antibody tests, but does that mean we shouldn't take any action? Right? At what cost, both ethically and practically, is it to continue to wait 2 years later to find out that we had 2 years of immunity? Are there ways to learn and watch and continue to modify in the near term? And in practice, I'm beginning to hear, to some extent, people beginning to act in this way, that thinking about ways in which in these settings they can try to reduce new risk, and happy to talk about that. So to close up, COVID-19 has high or not relatively fast spread, elevated fatality rates, and unfortunately asymptomatic transmission, irrespective of what WHO says, that increases the epidemic potential. Interventions have made a huge impact, but in some places, I would just say this has been implemented slower or less effectively than it should have been. Even if this big peak has been averted, right, we remain almost entirely immunologically naive, which means we need long-term strategies. And we need to think about testing. And my key emphasis here at the end is that both PCR and serology are needed at scale, and they're not just passive metrics to be put into dashboards. They should be used as a form of reducing new transmission. And in doing so, my hope is that many imperfect strategies that on their own won't be able to solve the problem can together add up to control, whether it's mask, contact tracing, and also this concept of shield immunity. And with that, I'm done. apologies for running a little bit over, and thank you for your attention.
Woo.
Happy to take questions.
my single little clap. Thank you so much. That was a really great talk. So if anybody has questions, they can either unmute themselves or write them into the chat. And I think we'll take, you know, about 5 or 10 minutes, depending on how much time you have, Josh.
Yeah, I'm fine. And again, like I could be here even till 1:30. I realize that's a lot of people's time, but I will hang out. And again, sorry for going a little bit late. There's always so much here going on with COVID-19, so it's hard to.
I know.
Josh, you're totally good. You're totally good. Yeah.
Chris, you said you had a question?
Sure. Josh, the talk was great. Could you go to the New York Times cartoon from the very beginning?
Oh my. Okay, that's gonna. I'll just hold the. You can ask your question while I hold.
Okay.
The left button.
No, I was thinking about this when we first saw it, and you know, there's that big like uncertain region, the rectangle in pink, maybe that we weren't really sure, you know, where it was, and so. So there's lots of empty regions in this plot, and I find it really interesting, and I'm going to ask naive questions because I don't know epidemiology very much. But so I sense that there's the left-right behavioral change axis, and you know, like we can shut society down to move to the left, or we can act like ideal gases and go to the right. And then there's the genetic viral information that's sort of the north-south, up-down axis. And you know, we couldn't really have stuff in the top right of this picture if, you know, we're going to be here because, you know, that would be too dangerous. And I'm wondering, it seems kind of like it's low dimensional, like there's maybe like a few regions or some kind of curve here that's being explored by nature. And I don't really have a great question to ask other than to say, can you tell me why you think that it's not sort of more looking like, you know, randomness, why it looks to have kind of either clustering or, you know, particularly like I would call it like a manifold of places where diseases land in this picture?
That's a big question, and it's a hard one. Let me try to say a few things, and I don't have a conclusive answer. I mean, there's certainly notions of these evolution virulence trade-offs that people have made, and there's almost no evidence. There's very little evidence to support them. So there have been some ideas, well, there's a trade-off between, let's say, transmission and how bad it is. So the diseases in some ways kind of play along these axes. And I think that you're kind of hinting at that trade-off that might put you kind of in this kind of shape. If I look at one in particular, you know, again, with respect to these numbers, and this is on average, and so we might ask the question about super spreading events, but if I hadn't shown you measles or even chickenpox and just kind of focus around the 0 to 5, I might say, well, it can go anywhere in that box, right? So then it gets a little bit more complicated.
Yeah.
And Ebola is interesting too, in the sense that what is the basic reproduction number for Ebola? That when diseases, if it's possible, depending on the nature of them, to identify them early, right? And this really has to do with are symptoms and transmissibility linked, then it's very hard for that to have, and it hasn't had, let's say, global effects in terms of spreading out beyond the 2014-15 case in the tens of thousands of cases. Before it was hundreds, whereas respiratory diseases got to many, many more people, often because even with many more fatalities overall, just because the individual fatality rate is so high, your ability to move is so high. So once you start going up, it's very hard for you to imagine you can get to the right unless you have some sort of thing that is, you know, has this asymptomatic route and you don't know, and so on. And then we also have the time scale. I mean, this fatality rates has to do with time scales too, right? So here we're not including things that maybe over a very long lifetime may affect, you know, sort of increase or decrease lifespan. We're often thinking about this in terms of an acute infection. So I don't have a great answer there. I'm just cautious about thinking that there's a fundamental trade-off, just because, as you said, society can move this x-axis quite a lot. We can, with some therapeutics, move the y-axis, but I do think that when things get up in the fatality rate, it's hard to move, for them to move very far to the right, though obviously smallpox is that's a pretty bad counterexample, right? So,
Josh, could I just mention,
Thanks.
I mean, there's one pandemic that never finished, right? That's never finished, which is HIV.
Now, HIV one is the one I was thinking about as I was speaking, in part because when we think about fatality rate and we think about timing, right, it's still ongoing, but now it's being treated. And so now it's very different, right? That's the fatality rate. First of all, it wasn't in an acute phase, it was in a long phase. So we're talking about lifespan loss. But also now it's, at least in certain parts of the globe, something that can be lived with, right? And
but until that point, it was somewhere out there in the, it was a nasty. And bubonic plague, bubonic plague, I don't know.
Right. So there's some that are very bad, but I don't know if there's any universal, but there's a lot of scatter here, even between 0 and 5 across the board.
So we have a couple of questions in the chat. I can read out. So with the incomplete data, in addition to the speed, size, and strength, R0 is estimated using classical and Bayesian methods, which are dependent on distributional assumptions with little sensitivity analysis. What is the true distribution of R0 to get CI with true coverage probabilities? What strategies should, I believe this should universities implement in the future?
Whoa, universities? Was there a different part there?
Yeah.
Okay, that may be a different question.
Yeah.
I mean, if the university can implement anything in the future, that would be itself a miracle. So that we maybe need to put that to a different box of questions. Actually, I think that's a very interesting question, but I think we should separate them. Okay. So I will say that in terms of what we've done here, we try to take distributional assumptions and then in a parsimonious way balance them, saying that there is some unknown growth rate or unknown generation interval, and then try to ask what are the effects in some sense of doing the sensitivity analysis that that person wanted us to do, which is imagining if alone we had uncertainty in generation interval, what is the effect there? If we had uncertainty in the squared coefficient of variation, right? And so I don't think I have, yes, I do have these labels. Actually, this is all together, and this is just looking at growth rate, just looking at variation in the generation interval. So we're actually doing what that person wants. He's trying to decompose drivers of this basic reproductive number. There is a big caveat here. We can do this, but there is a danger that, let's say study 2 published 20 other studies using all the same data, right? The studies themselves are not independent. So I don't think we have a conclusive decision on how do we deal with, if many groups start to focus on their attention on one particular thing, we would overweight their particular latent assumptions. So we have made, an effort. We are not at a point where I think vis-a-vis these estimates, we're in a Nate Silver-like poll averaging, and maybe even Nate Silver isn't in a Nate Silver-like poll averaging scenario. Others know better, meaning we are trying to treat each as being independent in some ways, even if they're often dealing with the same data, and they're just making different independent assumptions. But if a whole bunch of people started to make the same assumptions, then we'd be stuck with that. It would reflect the consensus of the community, not something fundamental. So I think to really get into this, we have to do contact tracing and look carefully at the time in which we think someone's infected. These generation intervals are much harder to estimate than our serial intervals. So maybe I should really answer this question by pointing out that a serial interval, which is the time, which usually what you can measure, that person was the infector, the infected had symptoms, what's the time, which can be negative or positive. Generation intervals, when was I infected? When is that other person infected? Must always be, the time must always be positive because of causality. We can measure serial intervals, but we often want to use generation intervals. There's a paper that we have out led by Songwoo Park that tries to reconcile the two. It's on medRxiv, and it's really tries to talk about the right way to think about serial intervals during an epidemic that you end up getting the right thing. So that was maybe a 3-part answer. Universities, I don't know. We have different problems there, but I don't know. That may be a different question.
So I think we'll take the last question that's in the chat. They're asking what your thoughts are about Sweden, just sort of given the limited closures and yeah.
So if you look vis-a-vis other countries in Europe, Sweden's strategy has been worse, right? Just objectively speaking, in terms of fatalities. What I guess what I am not sure about, and I think Laurent, I'm interested to hear what you think. We're also thinking about other ways in which behavior or variations in susceptibility or transmissibility or so on, all of these things point to the possibility that the final size is much less than the herd immunity size. There's a couple preprints on this. Laurent, I think you have a preprint on this very topic.
Unfortunately, I think he had to jump from the call, Josh.
Okay,
Sorry.
fine.
Yeah.
But anyway, he had also a similar thing. So the thing that I don't think we know is, and effort needs to be put there, is depending on interactions and depending on the nature of susceptibility and age-dependent mixing and so on, where is the point at which we're going to begin to see essentially decreases in new transmission because of this dispersion issue, right? And the flip side, and I'll really just credit Laurent for when he corresponded with me, the flip side, of course, of networks is that can even go the other way. So if we take individuals who are well connected, and when they get infected, we remove them and replace them with new individuals who themselves are well connected. And you know, that's like taking your core service worker, they're sick, put someone else that is susceptible, then you actually can drive things the other way, because you're essentially correlating degree, right, with being susceptible. And it's the opposite of a shield immunity strategy, which we're trying to increase interactions correlated with being recovered. So the more that I think we drive interactions away from high networked interactions being related to being susceptible or being, and instead move them more into those recovered status, whether through active measures, then I think we have a better chance. But with respect to Sweden, you know, they are already in some sense where public health officials have regretted some of their strategies. I think that other countries, including the United States at the state level, we're about to face a reopening. Different states are going to do it differently. But I think a lot of this will depend on individuals rather than state measures. I honestly do. People are worried about getting sick. The challenge then is that once it becomes individual decisions, then socioeconomic disparities become huge because everyone's worried about being sick, but some people have the ability to make a choice that others do not have. And so the thing that I think we need to be mindful of is moving forward as we open up. How do we take a strategy, whether it's shield immunity or mask wearing or stratified work schedules, and how do we make these choices so they don't exacerbate what are already socioeconomic disparities hitting some communities much worse than others? And if we do that, I think we're helping everyone, including the community that has been thus far disproportionately impacted. So I don't think there's one answer.
Say, Sweden hasn't, you know, just to your point, I mean, sort of this suggestion that Sweden's like its own little isolated, you know, group of people who are behaving in just this one Swedish way. But of course, they're completely influenced by what's around them as well. So there's, and they put some measures in, right? I mean, some schools, some years of school were closed and so on. So they did have some measures, but even so much worse than the other Scandinavian countries.
That's right. I mean, that's right. You can look per capita at other Scandinavian countries and you can see different outcomes. And there are other things too, though, you know, some places, it's going to be hard to deal with the fact that certain population densities in areas that will just be harder to try to make these changes, because if you have to get to work on public transportation, that just changes risk. Even if someone has good intentions and tries to act early. So, you know, we're going to be fighting for a while with this, and I think that's maybe the last message. We should not necessarily wait for these pharmaceutical interventions to come. It's going to take a long time. So we have to continue to find and leverage, maybe creatively, in ways that traditional public health would not think of shield immunity as a strategy, or mask wearing ubiquitously as a strategy. But we have to think about these things to try and get back to work safely while also minimizing risk moving forward.
So Josh, can I say a million questions? Maybe I'll just email them to you. But one thing, so you've done this work from the start, trying to, before serological tests were really even being talked about. And of course, as you said, we're still struggling greatly with them. But, getting people back to work, right? I mean, and in my courses over the years, I mean, this is what I've said, oh, look, dynamics are incredibly unpredictable. Here's the history of things. It's really just really difficult. And the models are sort of simple and, they tell you things. But then, it does seem that there's been an absence. I mean, it's very difficult of modeling the economic aspect, and so, right, there's a lot of epidemiological outfits like, here's my model, blah, 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 and this is what's going to happen, but there's just nothing, going forward in terms of the economic disruption. Very difficult thing to model, but it leaves us, I think, as scientists, really open to dis-narratives, and partly because we're either going to overreact or underreact, and we've kind of done both now.
Yes, and sorry, I agree. It's why we've worried about this from the beginning, and also knowing something about SARS-1 and MERS, my expectation had been that there was reason for optimism with respect to immunity, that it wasn't going to be like the seasonal beta coronaviruses, which had a very short period, and so on. And I remain optimistic in that sense. But you are right, because if we only focus on this one thing, what are the other costs? And there are real costs. Mental health costs for other diseases, people not going to the doctor, not being vaccinated for other childhood diseases. There's all these other knock-on costs. And if we don't take these into account, we'll be right on one thing, but we'll be wrong in so many other ways. And I think we have to really start facing the fact that this is part of a larger, you would say, complex system, but it's certainly part of a larger system. We can't just optimize for this one thing. I'm agreeing, basically. Yeah.
Great, thank you so much. I think we're out of time, but this was an amazing discussion and a really great talk. And we really appreciated having you here, Josh.
Thank you so much. Thanks